In this video, we're going to begin talking about derivatives and integrals of vector functions. Right, so we already know how to compute limits of vector functions, and we know how to deal with continuity of vector functions, and those will both be useful here. So to define the derivative of a vector function, we're going to look back at the derivative definition for scalar functions in Calculus 1 and just extend it in the most obvious way possible, and that is just by replacing the function itself with a vector function. So we're going to define the derivative of the vector function r of t, which is going to be denoted with either as r prime of t or dr dt, right? The same two notations, or the same two principal notations we use in Calculus 1. Is defined as follows. So r prime of t is going to be the limit as k approaches 0 of r of t plus k minus r of k all over k. Now you might recall from Calc 1 that we usually define this limit as the limit as h goes to 0. In the context of vector functions, h typically represents the third component function of the vector function, and so to avoid confusion with the notation, we chose to use k here. But of course we could use anything else. We just don't want to use f, g, or h since those letters are reserved for other things. So this is our definition of the derivative. So we're first going to take a look at the geometric meaning behind this, and then we'll look at how to actually compute the derivative of vector functions. Before we go on to compute derivatives and to figure out how to compute derivatives of vector functions, I want to take a moment and look at the geometric meaning behind the derivative of a vector function. For scalar functions, we know that the derivative gives the slope of the tangent line or the slope of the curve at the particular point. So we want to look at what the analogous interpretation of the derivative is in terms of vector functions. Right? So to do that, we're going to start off with our three-dimensional coordinate system. So here's our x, y, and z axis, although we really we're not going to need those axes in this case. Just need the origin. And so here we have some vector function r, and that vector function is going to sketch out a space curve, which we'll call c. So I'm going to draw that curve in here. And that curve will look can look something like this. So this will be my curve c. And I want to think of this as going in this direction. Right? So the curve is being traced out from left to right on the screen as t is increasing. And so for a particular value of t, when I substitute t into my vector function r, I'm going to get a point on this curve. And so let's say when I pick my value of t, it gives me this value, this point right here. And so this vector, as I've drawn it, this is the vector r of t, this blue vector here. Now the other vector that's in the limit definition of derivative is r of t plus k. And so I want to think of k being a positive number here. Of course, k could be negative, and that's fine too. But if k is positive, and the curve is increasing in t from left to right, then r of t plus k is going to be some point on the curve that comes to the right of r of t. And so, for example, maybe it's this point over here. Right, so this would be r of t plus k. Now, if I want to take the difference of these two vectors like we do in the definition of derivative, we take r of t plus k and subtract r of t, what we get is this vector here that goes from the head of r of t to the head of r of t plus k. Right? So this vector here will be r of t plus k minus r of t. Right? And that we can think of as the secant vector. Right? It's the vector that goes between 2 points on a curve. Right? And so now what we want to do is, just like in Calculus 1 when we have a secant line, we can drag this point, r of t plus k. We want to take the limit as k goes to 0. So we want to drag this point back along the curve until it's really, really close to the point r of t. And of course, if we drag the 2 points exactly on top of each other, it would not make any sense because we would only have 1 point, and the vector needs 2 points to be defined. So what we get, though, is we get a vector that this limiting process will get close to, and it basically is a vector that will continue off in the same direction as the curve at that particular point. And so this purple vector that I just drew will be r prime of t. Right? And so we can think of this as a tangent vector. It is a vector that indicates the direction of the curve at that particular time. And just like with curves in two-dimensional space, it gives the exact same idea, except now we're in 3 dimensions. So now that we know that the derivative vector is going to tell us the direction that the curve is moving at a particular instant in time, the next step would be to figure out how to compute a derivative vector without having to set up and compute a limit each time. And so to do that, we just work through the definition of derivative along with the understanding of limits that we've discussed in the previous video. So our goal here is to compute r prime of t. So r prime of t, we know by definition, is the limit as k goes to 0 of the vector r of t plus k minus the vector r of t, all divided by k. So now we can go back and rewrite these vectors r in terms of the component functions f, g, and h. So this will be the limit as k goes to 0 of f of t plus k, g of t plus k, h of t plus k, minus the vector r, which is just f of t, g of t, h of t. And all of that will be scaled by k. Now we can go ahead and subtract those vectors in the numerator and then divide each component by k. And doing so yields the following. We get the limit as k goes to 0 of the vector. The first component is going to be f of t plus k minus f of t all over k. The second component is going to be g of t plus k minus g of t all over k. And the third component is going to be h of t plus k minus h of t all over k. All right, so this is just vector algebra, vector subtraction, and then scaling a vector by a factor of 1 over k. And now I have a limit of a vector, and we know that this is the limit of each of the components. So this is limit as k goes to 0 of our first component. Limit of k goes to 0 of our second component. And the limit as k goes to 0 of our third component. And finally, each of these 3 limits and the components of this vector we should recognize as being Calculus 1 derivatives. This first limit is the derivative of f, so f prime of t. The second component is the derivative of g, so g prime of t. And the third component is the derivative of h, which is h prime of t. Right? And so if you ignore all the work in the middle, which we need to get the final result here, what we've just shown is that the derivative of a vector function is just the vector whose components are the derivatives of the appropriate components of the original vector function. So we just need to differentiate the three components functions to find the derivative vector. All right, so for a quick example, let's say we had a vector function r defined with component functions t cubed minus t, e to the negative t, and natural log of t. And we were defining t to be in the interval 1 to 3. So if I want to find the derivative vector in this case, we just need to differentiate our three component functions. And so the derivative of t cubed minus t would be 3t squared minus 1. The derivative of e to the negative t is going to be negative e to the negative t. There is a chain rule there that makes that negative. And the derivative of 1 over t, or natural log of t, is 1 over t. And this vector is going to be defined also from 1 to 3 because the original vector is defined on that entire domain. Right? And so finding derivative vectors of vector function, the derivative vector function, is very, very easy. It's just applying Calc 1 derivatives in all three components. Right. Now, before we go on, we do want to make define a couple terms that will be useful going forward. So the first one is we're going to say that a vector function r of t is differentiable at a particular value t, or rather at some value t naught, if my three component functions f, g, and h are differentiable at t naught. Now notice that we're not using the word differentiable to define differentiable. We're defining the differentiability of a vector function in terms of the differentiability of scalar functions. Okay? Now the real thing that we need the one thing that we're going to need going forward is we're going to need to talk about a space curve being smooth, and that is related to this. So we're going to say, in addition to this, that the space curve C that's defined by this vector function r is smooth at t naught, so at this particular point, if the derivative vector r prime of t, so the function has to be differentiable there, is continuous at that point, and r prime of t naught is not equal to 0. Okay. Now notice that this is actually equivalent to f prime, g prime, and h prime being continuous. So each of those three being continuous, that will make r prime continuous. And I want them not simultaneously equal to 0. Right? And this will verify the last part, that r prime of t naught is not equal to 0. The only time that derivative would equal 0 is if f prime, g prime, and h prime are all 0 at t prime, or at t naught. So if at least one of them is not 0, then the derivative vector will not be the 0 vector. Right? Actually, now that I say that, I should be careful. When I define r prime of t naught not equal to 0, I really mean not the 0 vector, not the 0 scalar. And so going forward, this idea of being smooth is going to be important in a number of contexts. And it means a little bit more than the derivative existing. It also means that the derivative is continuous and not 0. So if we look at the example at the top of the screen here, we see that we have a derivative that exists for t between 1 and 3. And we also see that each of these three functions are continuous on that interval. Right? 3t squared minus 1 is a polynomial, negative e to the negative t is an exponential. And 1 over t is continuous when it's defined, and it's defined everywhere except for 0, but 0 is not in the interval 1 to 3. And so r prime of t is continuous at any value between 1 and 3, and we also will not get the 0 value, or the 0 vector in this particular case between 1 and 3, because, for example, notice that both of the second and the third components are never going to equal 0. Right? So this will be continuous at every t in 1 to 3. And it's not going to be equal to 0 for t between 1 and 3 as well. And so this function here, this r of t function that I wrote down at the beginning, this is an example of a smooth vector function. Right? It has a derivative which is continuous on the interval, and it is not equal to 0 there as well. So the most common application of derivatives in Calc 1 was finding the equation of tangent lines to a curve. And so that's what we're going to do here in three-dimensional space as well. So let's say we wanted to find the tangent line to the helix given by r of t equals cosine t, sine t, t. At the point square root of 2 over 2, square root of 2 over 2, and pi over 4. All right, so in order to find a tangent line or a line in 3 space, we need to know two things. We need to know a point on the line, which we're given, right? And we need to know the direction of that line. Right? And so in order to do that, we're going to use the derivative vector. Right? Now, before we do that, let's look a little bit at this point. I've been given a point on the curve, and in order to eventually what I'm going to need to do is I'm going to need to evaluate the derivative vector function, r prime of t, at a t value that corresponds to this point. And so one thing we need to kind of observe at some point is what t value gives us this particular point, square root of 2 over 2, square root of 2 over 2, and pi over 4. And so in this case, it's pretty easy to figure this out because one of our components is actually t. And so the third component in this particular function is going to always give me the appropriate t value. So this point here corresponds to a parameter value of t is pi over 4. Right? So I'm just going to record that because we can see it pretty quickly, and we are going to need that in a moment. Right? So now we have our point. We now want to find our direction vector of our line. And so we start by finding the derivative vector for our function. So we want r prime of t. Right? And so the derivative function, we just take each of the component functions and take their derivative. So the derivative of cosine t is negative sine t. The derivative of sine t is cosine t. And the derivative of t is 1. So our vector derivative function is negative sine t, cosine t, 1. Now to find the actual vector, the actual tangent vector at t equals pi over 4, I want to evaluate this function at t equals pi over 4. And so we want negative sine of pi over 4, cosine of pi over 4, and 1. And of course, that will be negative square root of 2 over 2, positive square root of 2 over 2, and 1. All right, so this is our direction vector. And so our tangent line is given by the following. So we take our given point for the line in vector form, so square root of 2 over 2, square root of 2 over 2, pi over 4. And we add to that t times the direction vector. Negative square root of 2 over 2, square root of 2 over 2, and 1. And then we just combine this together. So in the first component, we get square root of 2 over 2 minus square root of 2 over 2t. In the second component, we get square root of 2 over 2 plus square root of 2 over 2t. And in the third component, we get pi over 4 plus t. Right? And this particular line, we want t to range over all real numbers, or from negative infinity to infinity, however you want to record that. But this is the line that will be tangent to the curve and have the same slope as the curve does at that particular instant in time. So the next thing we'd like to do is look at some differentiation rules. Analogous to things that you might have seen in Calc 1. So things like the product, quotient, chain rule, kind of the analogous things for vector functions. And most of them are pretty similar, although there's a couple new ones based on the new vector operations that we've seen. So we'll start off with an obvious one, and that is if I take the derivative of a constant vector, c, we get the 0 vector. All right, so here c is a constant vector. Right, so this is analogous to the derivative of a constant being 0 in Calc 1. Right? We also have some scalar multiple rules that are easy to do. So for example, if I want to take the derivative of some constant c times a function r, then it turns out this is just the constant c times the derivative of r. All right, this one behaves exactly like it would in Calculus 1. We can bring out the constant outside of the derivative. Now, one thing we can do here that's different than in one-dimensional world, in one variable land, is that we can multiply a vector function by a scalar function f of t. So for example, instead of multiplying the function by 2, we're multiplying it by something like t squared. Right? And it's not f of t is not a vector. Notice I'm intentionally leaving the arrow off. It's not a vector function that I'm multiplying it by, but another scalar function. And so it turns out that this works much like the product rule in one variable calculus. So this will end up being f prime of t, which is a function in a scalar function, times the vector r of t, plus the function f of t, the scalar function f of t, times the derivative of r of t. Now again, this looks a lot like the product rule, but we have to pay attention to the scalar functions and vector functions and which are which. Okay. We also have the sum and difference rules, which I'm going to write as one rule. So if I have a function r of t, and I want to add or subtract to that a function s of t, and this is going to be a vector function, s of t. This is simply the derivative vector of, or derivative function of r plus or minus the derivative function of s. Right? So these are sort of the standard basic rules, the rules for constant multiples, or constant vectors, for scalar multiples, both with scalars themselves and with scalar functions, and the sum and difference rule. So our next step is to define the analogous thing to the product rule for the product of two vector functions, but we do have two different vector products to consider. So we have to write down two different rules. So the first rule is we're going to take the derivative of a dot product. So the derivative of r of t dot s of t. Right? And as you might expect, this is going to be the same as the product rule in Calc 1. So this is going to be r prime of t dot s of t plus r of t dot s prime of t. Right, so just like in Calc 1 with the product rule, we're going to take the derivative of one function multiplied by the other function, and then do it the other way, and then add them together. Right? And so this one is very nice. Now the cross product derivative works exactly the same way, but this one we have to pay attention to the order that we put the functions in. Right? We know the dot product, whether we did r prime dot s or s dot r prime, it doesn't really matter. They're the same thing, but we know the cross product, the order matters. And so if I have to take the derivative of r cross s, this is going to be r prime cross s plus r cross s prime. Right? And so we have to pay attention that the r vector is always the first term of the product, and the s vector is always the second one. Right? Now there is no analogous thing to the quotient rule because we have no analogous operation for division in terms of vectors. So quotient rule is left out because there's no context for it to work. However, we do have a chain rule to consider. So let's say I have to take the derivative of a vector function r, and r is itself a function of some scalar function f. And so we have r of f of t. And so the derivative here, just like with the chain rule, we're going to take the derivative of the inside function f prime of t and multiply that by the derivative of the outside function r prime evaluated at the inside function f of t. Now, I've written f prime first. That's a little unusual for most people. But notice that I did that because f prime is a scalar and r prime is a vector. And it's very common to put the scalars in front of vectors and not after. And so that's the only reason I listed it in this way. Right, so along with the ones from the previous screen, these are the various differentiation rules that we will need throughout the course. I'm not going to make any effort to justify any of these rules, but most of them are relatively straightforward if you apply the limit definition of derivative and then various limit properties and techniques. If you look at any of the product rules that we've defined here, the dot product or the cross product rule, if you look at how the regular product rule in single variable calculus is derived, this is done exactly the same way. And exactly the same thing works for the chain rule. So as an example of these properties, we're going to do an example that we're actually going to need in a couple weeks. So let's suppose that I have a vector function, r of t, and the magnitude of that vector function is equal to 5 for all real numbers t. Now, geometrically, what this means is that every vector that we get in this vector function has a magnitude of 5, which means this vector function lives on a sphere centered at the origin of radius 5. And so this, when we trace out the curve that's generated by this particular vector function, this curve will live on a sphere of radius 5. Now what we want to do here is we want to show that r prime of t is orthogonal to r of t for all values of t. So like I said, this is something that we're actually going to need later on. So the basic idea is if we have this curve that's on a sphere, then every vector given by that is orthogonal to its tangent vector, r prime of t. And so if we want to show two vectors are orthogonal, our goal should be to show that r of t dot r prime of t is equal to 0. All right, so if we want to show two vectors are orthogonal, the best way to do that is to take the dot product and to show that that is actually equal to 0. Right? And so in this case, we can't do this directly, but we can actually use derivatives to make this work. And so let's start with an observation. And that observation is that we're going to take the vector r of t, and we're going to dot product it with itself. So I'm going to take r of t dot r of t. And I know from dot product properties that if I take a vector and I dot it with itself, I actually get the magnitude of that vector squared. And in this case, that is 25. So r dot r is equal to 25, and that's for any vector on the curve C generated by this vector function r. It doesn't matter what the curve is, doesn't matter what value of C is. All right, so what I'm going to do is I'm going to take the derivative of this dot product. So on the one hand, the derivative of r dot r is going to equal the derivative of 25. Because r dot r is equal to 25, and the derivative of a constant is equal to 0. Right? Now this is actually nothing to do with what we've just been doing. This is actually calculus 1 once we do the dot product. That's r dot r is just a function of one variable t. However, we can also compute this d dt of r dot r using the derivative product rule for dot products that we just wrote down, which says that this is r prime of t dot r of t plus r of t dot r prime of t. Right, so this thing that we just wrote down, this is our dot product rule for derivatives of vector functions that we just developed or just stated. Right? Well, if we notice, r prime dot r and r dot r prime are exactly the same. And so when we add these together, we just get 2 times rt dot r prime of t. And we don't care which order the dot product is taken in. And so what we've shown here, since all these things are equal, we've just shown that 2 times this dot product is equal to 0. And so if that's the case, we can divide by 2, and we can conclude that r dot r prime is equal to 0, which is what we wanted to do. All right, we wanted to show those two vectors are orthogonal. And so by computing the derivative of the dot product of r with itself in two different ways, one using calculus 1, one using calculus 3, we're able to conclude that dot product is 0, and therefore the vectors are orthogonal.